1/8, right? 1/2 times 1/2 times 1/2. It's 1/8. I'm going to pull that out of the integral now. And then I have to do 1 minus cosine of 2x cubed dx. This is the part that I was telling you is going to be nasty. Because you got to cube that, right? That means you have to do 1 minus cosine 2x times 1 minus cosine 2x times 1 minus cosine 2x these would be what? So we did that earlier, right? That's 1 minus 2 cosine 2x plus cosine squared 2x. Y'all agree? These two together is this. And then I have to multiply this through, which is going to give me 1 minus 2 cosine 2x plus cosine squared 2x. That's the 1 getting passed through. And then when I go with the negative cosine 2x, I get negative cosine 2x times 1. When I do that times that, I get plus 2 cosine what? I'm doing this and this, so plus 2 cosine squared. Shit. Okay. And then I do the last one, which is this times this, which is minus cosine cubed 2x. And then I combine like terms together. All right, so what does this new integral become? 1. I'm happy I can integrate that. Okay, this cosine 2x, 2 of them, and then another one, right? So these are like terms right there. So I have negative 3 of those. Negative 3 cosine 2x. I can integrate that. I'm happy, right? You happy about that? Okay, how about cosine squareds? Got that one and that. I got 3 of them, plus 3 of them, plus 3 cosine squared 2x. I'm not happy about that. Because cosine squared, that's going to require the power reducing formula for me to do it, right? And I'm not done. I have my last term, which is minus cosine cubed 2x, right? dx. So recapping. Happy, happy, not happy. This is an odd power, right? Odd power, we peel one off, right? We peel one off, which leaves a cosine squared, which we turn into 1 minus sine squared. Didn't we start the class with odd powers? So we can handle that now, right? We can handle that with a power reducing formula. But all of this, I break this into 4 new integrals, right? 1/8 of this, 1/8 of that. Then these two I'm going to have to do a lot more work, right? So, ... I'm going to leave that open. I remember being in Cal 2, my professor gave us cosine to the 8th. Not on a test, just as a take-home exercise. And you want to talk about like having to keep track of constants and like, it was a mess. It was a disaster. But I can remember doing the problem. I had to write it sideways like this, across the page like that, because it was just so long and tedious. I won't torture you like that. But
what is the highest power you can give us on a
probably 10. Probably 10.
That's
No, I don't. I probably 4 probably would be the highest because time-wise it would take too long. But I recommend that you run through this problem completely. Okay, and in the homework there's going to be stuff like this. Just grind it out because it allows you to practice using the power reducing. Think about this. When I use this power reducing here, right? I'm going to wind up with a cosine 4x because I'm going to be doubling that angle again, right? Okay. I recommend you finish that yourself. How are we doing on time? 30 minutes still? Yeah. Okay. Let's go back to the notes, see where we are. Let's see where we are here. if you have sine to a power or cosine to a power where they're even, we're going to use the half angle, the power reducing formula, and the following identities, which I just gave you, to do the problem. All right? So does that note now make a little more sense? Okay. So these are your examples. So I did this one, right? I did this one. Something like this one, yes? This one I didn't do. Why don't we make that a take-home problem to be turned in next time? All right? It's cosine to the fourth, so we kind of already got it started, but there's one little caveat to this. We got a beta t in here. So you got to keep track of that beta when you're integrating, right? You're going to get like a 1 over beta. So that's a good exercise. Yeah, do that as its own problem. Turn it in on separate paper. Don't put it on the back of your notes. Just new sheet of paper. All right? Well, we have, is it raining? It's raining. We have conveniently avoided anything other than sine and cosine, right? So what if you have tangents and secants? Well, let's talk about what we already know. We already know the antiderivative of secant squared, right? So like cosine squared sucks if we have to integrate it because we got to use the power reducing formula. But secant squared is okay because it's just tangent, right? And also the antiderivative of secant x tangent x is just secant x. This is Cal 1. Derivative of secant is secant tangent. Derivative of tangent is secant squared. So if we ever see this or this, we can actually undo it, right? Also, we could show a very similar result that we had earlier. If we have secant squared of a linear function, we're just going to have 1 over a tangent. If we have secant ax tangent ax, we're going to have 1 over a secant ax. That 1 over a just has the same effect that it had with the sine and cosine. We have to be able to kill off the chain rule. So what's the strategy if we see secants and tangents? Maybe we'll read through this now that we have a little bit of an idea of what's going on here. If we are presented with an integral involving powers of sine and cosine, we can attempt... Oh, I didn't never change the... this is not attempt, this is attempt. Yeah, that should be tangent and secant. Oops, that's copy and paste catching up with me right there. All right, so here we go. If you've got a tangent to a power, secant to a power together. So if you see tangents and secants mixed with the power on secant being even, use a Pythagorean, what Pythagorean identity? Sine squared plus cosine? No, that's not the one they're talking about. This is the Pythagorean identity everybody knows, right? But aren't there two more? Do you all have them memorized? Do you have that one memorized? Yes? Okay, I don't have them memorized. I just have a way of getting to them, all right? So this might help you. It always helped me. I have that one memorized, all right? So to get the other ones, what you can do is just divide everything by sine squared right now. Just what would happen if I divided this by sine squared? 1. Okay, if I divided that by sine squared, I would have cosine squared over sine squared. What's cosine over sine? Cotangent, right? So this would be cotangent squared x. And then this, what did I divide through by? Sine squared. This would be 1 over sine squared. What's 1 over sine? Cosecant. So this would be cosecant squared. Cosecant squared x. That's one of the Pythagorean identities. How do you think I get the last one? Divide everything by cosine squared. So what's sine squared divided by cosine squared? Well, sine over cosine is tangent, so that's tangent squared. And then I'm dividing by cosine squared, right? So that's 1. And then 1 over cosine squared would be secant squared. So there are your other two Pythagorean identities. Oh, there's something crawling on me. All right, there they are. So we're going to use, oh, I had it right here. This is the one we're going to use, right? There we go. That's it, right? That's helpful though, right?
Yeah.
Okay. So we're going to use that one, and then we're going to let u be tangent. Let's do that example right there. So I have tangent to the fourth x secant to the fourth x dx. Remember what I said when I started class, that what we're doing here today, trigonometric integrals, is required to do trigonometric substitution, which is the next thing. When we do trig substitution, we're going to be doing some crazy stuff, and at the end, we're going to get like sine to the third cosine squared, and we're going to be like, yes, we can do that. You know? Like we can do that using this. Yeah. Yeah. All right, here we go. So do you see tangent and secant together? Yes, right? Do you see that the secant is even? Right? The secant is even. And because it's even, I'm going to peel off a secant squared. Keeping in mind that by doing this, that's forcing my hand. This part's going to be the du, which means u has to be what? Tangent, right? That means u is going to have to be tangent because my du that I'm peeling off is secant squared x dx. And that means everything else that you see over there needs to be tangents. They all need to be tangents. So we're okay with this, right? That's going to be u to the fourth power. Secant squared, how do we get that to a tangent? The identity, right? The identity was tangent squared x plus 1 with secant squared x. So I can replace that secant squared with tangent squared x plus 1. Just needs to be in parentheses. So this is integral tangent to the fourth x, then tangent squared x plus 1, and then secant squared x. I kind of didn't give myself enough room here. Oops, sorry about that. Any questions on where that came from? What do you think we do now? Just switch everything over to u. All right, here we go. This integral becomes what? U to the fourth. Parentheses. U squared plus 1, close parentheses. du. What are you going to do with u to the fourth times the u squared plus 1? Just distribute that u to the fourth through. U to the sixth plus u to the fourth du equals ... Because now we've got a power function, right? We've got a polynomial, and you just do, this is 1/7 u to the 7th, this is 1/5 u to the 5th, and then replace u with tangent. So this is different from what we did before with sine and cosine, because in order for it to work, we have to pull a secant squared off, right? Because the derivative of tangent is secant squared. So you can't just pull just a single factor of secant out. It's got to be the secant squared, which is why this is what we do if we see secant to an even power. We can always pull an even number of factors out. Let's look at the next one. Tangent to the fifth secant cubed. So we know what to do if the secant's even, but what if the secant is odd? tangent to the fifth, secant cubed. How are y'all feeling? Are y'all tired? This has been a long week? Yeah. All right, so we do not pull out a secant squared because it's not even, right? I mean, we could pull a secant squared out, couldn't we? The problem with pulling a secant squared out is that we would have a secant to the first power in there, and that we don't have a Pythagorean identity for. So instead, we're going to use the fact that, well, in the previous problem, u was tangent, the derivative was secant squared, right? The other thing we could have is have u be secant, and the derivative would be secant tangent, right? So why don't we pull, or peel, or pull, or however you want to say it, why don't we pull off one factor of tangent and one factor of secant? Do you see why I'd want to do that? If I peeled off one factor of the tangent, one factor of the secant, then this right here is my du. Right, my du would be the secant x tangent x. And u is equal to, what would the u have to be if that's going to be my du? Secant x. So this right here, that's du, that's good. This right here, that's going to be u squared, yes? And the tangent to the fourth? The identity, but then squared, isn't it? Like, you have to look at tangent to the fourth as being tangent squared x squared. That's tangent to the fourth. I'm doing this on the side. What is the identity for tangent, though? Tangent squared, sorry. Secant squared x minus 1. You have to just kind of move things around. Yes? Y'all know what I did there? Okay. This is this, and then the square just comes along. So we can rewrite the problem now. This is integral. It's secant squared x minus 1, that quantity squared, times secant squared x times secant x tangent x dx. There we go. Keeping in mind that this is our du here. So we should be able to rewrite everything. This becomes integral. What? U squared minus 1 squared times u squared times du. And how would you handle that? So you're going to do this first, right? U squared minus 1 times u squared minus 1, then pass a u squared through everything. Then integrate each one term by term, and then replace u with secant x. You didn't think that this could become any more exciting or fun, did you? Right? And then look at the next note. There are other cases which aren't as obvious. Like these three. Yes? Thank you for asking. The original identity that I tried to illustrate that I came up with over there was this one. That was the one where I took sine squared plus cosine squared equals 1. I divided everything by cosine squared. And everyone, I think, agreed with me on this? Yes? So then all we're doing here is we're just subtracting 1 on both sides. Yeah? No, Sophia, it seems like you're just being agreeable. Okay, look, you believe this identity is true? Do you see it on your formula sheet? That's not what I gave you? Right? I derived 2 of them. Yeah, remember, in the Pythagorean identities, there's 3 of them. There's sine squared x plus cosine squared x equals 1. And then there's 1 plus cotangent x equals cosecant squared. Yeah? You sure?
Yeah, I got it.
Okay. If Sophia's lost, then I'm concerned. All right. Here we go. Look at these. These are not as obvious. So let's do the first one. Hey, wait a minute. The antiderivative tangent, that's on your formula sheet. Isn't it? Okay, then we don't need to do it. How in the world did they get that formula? That's tangent, right? Yep. That's tangent? Let's let u be cosine x. By the way, what does your formula sheet say the antiderivative of this is? Isn't it like natural log of secant x? It's not on your formula sheets? It should be. It should be on the right-hand column. Number 12. It's formula number 12 on your integral formulas. What reference page is that?
6.
Natural log of secant x, right? Let's see where that comes from. You rewrite tangent this way, and then we let u be cosine x. du would be negative sine x, but I don't have a negative sine x on top, do I? I have a positive. So I just multiply both sides by negative 1. That fair? This integral now becomes, the sine x dx was part of my du, right? So this is 1 over cosine, which is really 1 over u. So this is 1 over u, and then I had a negative out front du. Is that okay? Okay, that's a negative natural log u. Absolute value of u plus c. All right, what's u? Cosine x plus c. That doesn't match the formula. Did I mess up? No, what does the property of logs, you have a negative out front, right? Doesn't that mean you can, if you have a number in front of a log, you can push it up as a power? Or if you have a power on a log, you can bring it out front? So if I bring this up top, natural log, this becomes absolute value and it becomes cosine x to the negative 1. Raised negative 1, not the arc cosine. It's this expression to the negative 1, which means 1 over the expression. And what is 1 over cosine? Secant. All right, so this one we did not use any of the methods that we did in the previous parts. It had a tangent. We just rewrote tangent as sine over cosine. So that's where the formula comes from. So I could have shown you that problem right there. I could have shown you that when we first started u substitution. Right? When we first started u sub, I could have proven this to you. Secant x. Is secant on there? What is the antiderivative of secant x? Okay, that seems ridiculous. Let's look at this one. This is by far the most interesting problem that I'm going to show you today, in my opinion, because there is no easy attack for this one. There's just not a way to go about it. I mean, you can try all sorts of different methods, integration by parts. You can try rewriting it as 1 over cosine. You can try a bunch of different things, but it's just not going to happen. All right? So somebody suffered through this. When I say somebody historically in the past suffered through this until they finally came up with this kind of like idea. It's not my idea, okay? I don't claim it here. I'm just showing it to you. And I think this is going to give you some indication of the suffering that mathematicians have gone through in the past. They realized a hidden 1 right here, that there's a 1 next to it. Okay? Like next to everything multiplied is a 1, yes? Here's the 1. Secant x plus tangent x over secant x plus tangent x. What? What? So they just realized this right here is 1, right? Do you agree? We would never come up with that on our own. We would just, like, never just, yeah, let's just put that in there. But look what happens. If we multiply through the top, we get secant squared x plus secant x tangent x all over, the denominator hasn't changed, secant x plus tangent x. I'm only showing you this just to show it to you. You're not going to be like tested on this, or I'm going to have you pull some crazy thing like this out of nowhere, you know. I would never expect it. But this you can hopefully appreciate some of the magic involved. Okay, you got that? Y'all with me? Now, why did this person come up with that weird 1 to multiply by? Well, here's why. Just make a basic u substitution now. Let u be the denominator. And isn't it awesome what happens when you take derivative of that? What's the derivative of that? So what's derivative of secant x? Secant x tangent x plus what's derivative of tangent x? Secant squared x, right? And do you see that anywhere? It's the numerator. It's the numerator. So you know how with substitution you're trying to say, do I see something in its derivative? This person like forced it to happen. They're like, I'm going to do something to make something in its derivative show up. And I'm sure that they practiced different things first, tried different things, and finally got this one to work. Do you see that's not natural? That's not a natural move? Okay. But now that you've seen it, you can appreciate how awesome of a move it is. And so now this integral can be rewritten how? 1 over u du. And the antiderivative of that's natural log of u. And what's u? Secant x plus tangent x plus c, which is the formula in the back of the book, or in the formula sheets. Except they use u, right, instead of x. Pretty awesome. It's weird because if this was secant squared, it's trivial, isn't it? Antiderivative of secant squared is just tangent. If it's secant cubed, turns out to be pretty trivial too. If it's secant to the 4th, it's trivial because we can peel off the secant squared. It's secant to the 1st power that's the most problematic. Secant to any higher power, we can kind of knock them out pretty easily. I'll show you. The last example there of the weird ones is secant cubed. So to get secant cubed, what you do is you rewrite it as secant squared x secant x, like that. And then you do integration by parts. So you go like this. dv is secant squared x, dx. U is secant x. And then what would the antiderivative here be? Tangent, right? So I would have tangent x. And then this right here would be secant x, tangent x, dx. So my new integral would have what? Tangent squared and secant? Yes? Maybe we should finish that. You know what? I'm not going to finish it. I'm going to leave it as an open thing for us. We could continue, but I can't finish it in the time I have. But it can be done. I just wanted to show you how we would approach that problem. We could finish it out with this. Okay. Let's see where we are in the notes. I want to end class. Don't worry, I'm going to end it. But let's just make sure that we got to everything. Does anybody happen to have the textbook with them? Okay, I'd like to, if I could, look at it real quick just to see, in the homework I give you the first 61 problems, right? I'll get this one. I just want to see how many of those you can do right now. This is 6-2. I have good news. You can, in theory, you could do the first 36. Some of those towards the end of those would be kind of tough. But, you know, at least the first 25 of those. And I think I did the video solutions for these, and I think I did every single problem. So yeah, it's a lot of work. Okay, anything else we want to wrap up? Oh, I wanted to look at the notes. So yeah, that was it. Secant cube was my last example. And then the next thing that we're going to come in with next week on Tuesday is trigonometric substitution. Okay, that'll be it. After we master the above concepts, we use them along with an interesting type of substitution to find antiderivatives of some rather complex functions, like this. Yeah. These things. All right. Focus on, what's in front of you right now, okay? Which is the beginning part of 6.1. Let's not look too far ahead here. What the heck is that? All right, have a good weekend, everyone. Who am I meeting with? I'm supposed to meet with